Okay, we'll start this session. Good afternoon, everyone. I'm Anay Shambikar, PMRF and PhD candidate from Aerospace Engineering, IC Bangalore. Welcome to this extra session for the NPTEL course Dynamic Behavior of Materials. This course has the code NOC 24ME102. In this session, we'll be going through a couple of applications in a little more detail. So at the end of this course, wherein we have studied dynamic fracture in week 12 as well as shear bands, we have gone throughout this course. We have gone through a large number of topics which concern deformation in materials, quasi-static and dynamic deformation. Similarly, what different types of waves you have, going from elastic, plastic, shock waves, and then throughout all these different topics we have somewhere along the lines we have always spoken about some applications, some potential uses wherein these concepts as well as these physical phenomena can be put to use. So herein in this session we are going to look at two civilian applications in detail and try and apply what we have learned into that context. So the first one is related to explosive welding. So as you have already looked at before, but I'll recap it. So, explosive welding can be used in a couple of cases. When suppose you have a large surfaces needed to be welded, or you want to weld metals with different with large difference in their melting temperatures. So those that cannot be achieved conventionally. So this is a very niche market, so to speak. So it's not like the popular the well-known technique going around when we talk about welding. That would be a normal, say, arc welding or stuff like that. This is a very niche scenario that we are looking at. And it works on the following principle. So the principle of operation is as follows. You have an inclined impact occurring between two metallic objects, and what this does is this inclination helps create inclined impact creates a jet that cleanses surfaces of all, say, if there are any surface contaminants. Because of the impact, a jet of the material will be created. It will start flowing and it will remove any contaminants that are sticking on the surface and forces the objects into direct contact. As a result, the pressure of what exactly happens is there is some explosive powder which will be placed upon, say, the top plate, and there it will be detonated. So there will be a pressure due to the explosives acts upon these two clean and hot surfaces for a time sufficient for bonding and cooling to occur, which in turn, so this creates weld surfaces. Okay, so far straight simple this thing. So we look at two particular configurations in this. So like two common configurations, there can be more. But suppose the first is tubular configuration. In tubular configuration, what you have is you have a explosive, then you have the inner plate or inner tube, and draw the explosive in this dotted line. You have a detonator on top with the two polarities. This is your inner metal. After a gap, you have your outer metal. So this is like a cylindrical cross section. Okay, and what you have is, so the top view would look something like explosive, inner, this is the inner plate, then you have an outer plate after a gap, which goes like this, something like this. Right, so once you have detonation occurring here, so the explosive will be detonated from top, and that will, you can imagine that the inner tube will be forced outward onto the outer plate, impacting it, and you will have a situation which looks like this. The outer plate, this is part of the inner. This is the explosive unburned. You have a detonation front here. So the outer plate starts, inner plate starts impacting outer plate, and you have a welding occurring here. Another type of configuration which is much more popular is the plate configuration. Inside the plate configuration, as the name suggests, you have two parallel plates. Draw it. You have a base plate, you have a flyer plate, you have a standoff. This is flyer plate. This is the base plate. This distance is the standoff distance. You have explosives on top of this. Stands into a plate like this is the base plate. Stand up. Okay, so explosive base, I'll write here fire plate. This is the bed of explosives. When detonation occurs, you have again similar thing. So my base plate. This is my fire plate. Your explosive somewhere here. This is the detonation front, right? And here you have a wavy this thing. So this, if we zoom into it, this looks like a jet. There is a waviness. This is wavy texture at the place of joining. This is the jet. Okay, so if we look into the parallel plate configuration of it, it can be approximated as this. It's a dynamic bend angle beta. This is collision velocity Vc. This is the detonation velocity Vd. And this whole thing converges downwards with some impact velocity, plate velocity Vp. So if one were to draw it in a trigonometric manner, you have Vc, the collision velocity equals detonation velocity for a parallel plate impact. Then this is Vp. This thing is, this is the dynamic bend angle beta split into half as beta by 2. Right, so for parallel plate impact, sorry, for parallel configuration of welding, you have collision velocity Vc equaling detonation velocity Vd, and beta is the dynamic bend angle. Then from this plot, you can see that half of Vp, so I'll draw the diagram again. Vc, Vp, Vc. So whole thing is beta. Half of Vp is equal to Vc sine of beta by 2. For small bend angle, small dynamic bend angle beta, sine of beta by 2, approximately half of sine of beta, which means VC, sorry, Vp is equal to twice Vc sine of beta by 2. This is what the equation we have from here, and then you can just substitute the other one for small beta angles. Vp is approximate Vc sine beta. Right. So this is how the different velocity components are related to each other in the case of a parallel plate explosive parallel plate configuration in explosive welding. However, there are certain conditions that need to be fulfilled. So we'll write those down. Conditions for explosive welding. So the first condition is jetting. So you need a jet of material to be formed. So without that, that whole material uh, impacting the other, the metal impacting the flyer plate, impacting the base plate, and removing any surface contaminants and heating up and coming together, that will not occur. So jetting is required for explosive welding, and we also see that no jetting possible if collision velocity Vc exceeds elastic wave velocity. Shock front produced at the impact point travels with the collision front. So both shock front and collision front travel together, and it depends on the dynamic bend angle. Next, you have there is another condition called as critical impact pressure. So there is no jetting below critical impact pressure, which is a material property. From Bernoulli's equations, we can find the pressure for hydrodynamic flow, which will be nothing but half of rho into UP square, and substituting the particle velocity UP with velocity VP that we have here for the plate, you can get an equation of sorts. Third is maximum impact velocity. So the flyer plate kinetic energy, excuse me for a moment. So the flyer maximum impact velocity, so it is the flyer plate kinetic energy which converts to heat upon impact. As a result, some melting occurs. If impact velocity is too large, lot of melting implies large melt thickness, which in turn implies interface will have no strength. You need some melting, but too much melting will rob the interface of its strength. Fourth condition is critical flow transition velocity. Again, we have seen that in the zoomed in microstructure that you can have a sort of wavy texture where the flyer plate will weld with the base plate. If that wavy structure exists, the bonding is better, there is more strength to that bond. As a result, that is what we want, that becomes desirable. So, above a certain collision velocity VC, interface goes from straight texture to wavy texture. And there is no specific, like widely agreed theory that this is the reason why. But one of the theories is one possible theory is due to Kelvin Helmholtz instability, where there is a velocity discontinuity at the interface between the two materials that leads to generation of that wavy texture. So combining all these four factors, we get a window. So on y-axis you have the dynamic bend angle, on x-axis you have collision velocity. As we mentioned, there is a critical flow transition velocity. So I'll write this transition velocity. You want to be on the right hand side of this to get a wavy texture. On the left you will get a straight texture. Similarly, there is a minimum velocity for impact. This is your critical minimum velocity. This corresponds to the critical pressure. There is another this thing, excessive melt above this velocity, and you have no jetting and jet. So the reason that we want to restrict ourselves is to this reason. And go a little straight or wavy on the border, but basically all four factors combined together. So the straight line, dotted line is your fourth factor, which is the critical flow transition velocity. The right hand side line is your velocity for jetting. So like under that velocity you'll have jetting. Then you have critical impact pressure that is generated upon due to your impact velocity. Again, that plays a lower bound. Without that, you will not have any jetting. And finally, you have a maximum impact velocity above which you will see melting, which is the above excessive melt. So that shaded region is the basically zone of welding. So this is the welding range. Shaded that we wish to stick. It was, I think, derived by Man. That covers an overview of explosive welding. Next application is regarding shock consolidation using of powders. So shock consolidation. So one stage densification or bonding process. This is useful for creating rapidly solidified powders, both metals as well as ceramics. It involves very rapid and intense, so both rapid and intense energy deposition of shock energy on the resulting in interparticle bond. Example of the same is graphite to diamond synthesis. Another example is quartzite form of boron nitride. So the mechanism for continue it here. So the mechanism for consolidation in metals looks as follows. You have deformation and high velocity impact of particles. This results in you can have a filling of interstices. The particles are small enough, some of them are small enough. Another thing is you can have a breakdown of surface oxides. Here heating and melting of particle near the surface and your subsequent weld. You have a variety of processes involved that make use of this. So the first one is shock compaction, wherein passage of shock waves deposit energy near the surface. Second is shock induced chemical synthesis, wherein compounds formed uh, where you have a compound forming from a powder mixture. You can also have a shock induced phase transformation. So the experimental techniques regarding the same, quite so the first one is quite straightforward. A lot of you can think of it on your own. It's a cylindrical single tube. So you have a housing with made out of explosives. Uh, you may have a plug. You have another plug at bottom. This is the powder to be compacted, placed in the center. This is the explosive. It's the detonator powder. These two are plugs. Explosive central axis. Upon detonation, you have the top plug remaining same. Then go a little down. Then the bottom plug. So this looks like a detonation front. This say, compacted powder. Another thing is the cylindrical double tube. So here you have a larger setup. So setup. You have a detonator, two charges. You have a data sheet, a sheet, detonator, explosives, the plug, so plug. This is your, you have two cylinders here, one inner cylinder which is thinner, one outer cylinder. Inside the inner cylinder you have your powder. This thing is made filled with explosives. Explosive top plug. Then you have a bottom plug. You have a flyer tube. It's the powder container. If you look at it from a top view, you'll see like this circle containing metal powder. Then you have some gap before you get to the flyer. This radius is R0. There is a gap. This is a wet piece of container. Should be more circular. My apologies for drawing. This is powder. This is flyer. This is explosive. And this is the explosive container. So a double cylinder. And how it works is explosive detonated at top. Then you have a data sheet, creates uniform detonation front, and what happens is the external tube acts as flyer, the flyer tube that we have labeled in the diagram. It impacts internal tube, and this helps creates much larger pressure compared to a single tube setup. So this allows us to use low detonation velocity explosives as well. Okay. If you look at the material part, for this scenario, you see that in a successfully consolidated product, the interparticle regions basically melt are molten and solidified rapidly. So there's a rapid melting and resolidification, and this is generally seen more in metals than ceramics. And this rapidly resolidified microstructure is usually microcrystalline and amorphous, which means that we can see this in uh, can be seen in TEM micrographs as almost continuous diffraction rings. Because there is a big issue in shock consolidation. It's basically cracking of compacts. So whatever powder that we are compacting, if it already breaks, then it's a bit of a problem during the shock wave loading, and as a result, you may not have uh, like a solidified unified structure. So we do not want that cracking of compacts. It is usually more severe for hard materials, which is incidentally also the most potentially useful application. So for hard materials, creating a monolith is difficult. So if you can start off with powder and then use some sort of consolidation, not necessarily shock, but if you can use some sort of consolidation to bring the material together, then you have a unified structure made out of that hard material. So that cracking of compacts is a bit of a problem. And to minimize, we have two approaches. One is preheat the compact. This what this does is makes them soft and ductile than before. Another solution could be use shock induced reactions. What we have here is this creates localized heating near particle surfaces, which in turn enhances bonding. One theory we have is so how this whole process works. Theoretical aspect is a little unclear. So one of the theories that we have is something which was proposed by Graham, and it has the acronym CON, which refers to configuration then mass mixing followed by activation and then heating. Configuration refers to changes in configuration at the shock front. Mass mixing would refer to, so if you have an intense plastic deformation and localized kinetic energy leading to mixing of powder. High defect concentration seen, which activates powders and makes them more reactive. Finally, you have heating referred to intense localized heating. So, from a particle point of view, so if you have like an uncompacted powder to begin with, so uncompacted, so you could have this microkinetic energy, so wherein all the particles start filling the voids. Okay, you could have then friction coming up. Now approximating the particle as hexagons. So as they come together, they have their own relative velocities, start rubbing with each other, creating friction forces. We have got friction energy. You could also have some amount of energy being going into fracture. So if you have cracks being generated, you got fracture energy. Some amount of energy being used up in that. Could also have what is called as reaction bonding energy. Could have some reactions occurring. So what reaction bonding energy. Could also have melting. Melting occurring at the surface. You could also have say something like defect energies, and if there is some energy associated with collapsing of voids between the particles. So the important thing is that once you apply a shock wave through the shock wave loading through the material, as it passes, it carries its own energy, and then that energy will interact with the particles. Those particles, some of that will be used in kinetic energy, which will then be dissipated in the form of say friction. If the kinetic energy is too high, you could have dislocations, and eventually even fracture occurring within the particles. So again, some amount of energy will be used there. If there are some interparticular smaller particles which can undergo reactions, then those particles may also undergo reaction, and that in turn can both, depending on the type of reaction, can both absorb or release some amount of energy. Especially it can release if it's an exothermic type of reaction. All this to finally could lead to melting, or basically release of excess heat near the surfaces, which in turn leads to melting of the surfaces. So that melting would then resolidify, and you'll end up with uh, a rapidly melt and come resolidified consolidated product. So Schwarz developed a model, and how this worked was energy to melt. It evaluated energy to melt a certain fraction of particles. And from this energy, pressure can be calculated with a certain porosity. You can also use this model to calculate shock pulse duration necessary for a melting resolidification. So, and here the big assumption is shock wave energy provides energy for melting via total con- conversion to heat. So all the shockwave energy gets converted into thermal energy, which in turn provides us the melting part. So you can have shockwave energy. We can write as Es is equal to half E V naught minus V naught. So again, we have already seen this. I think the fifth chapter of the Martinez book. So you have half V naught alpha minus one. Where alpha is V double naught minus V naught. Similarly, you have melting energy plus heating. You need heating before melting to reach the melting point. Em is equal to Cp Em minus T naught, which is the again specific heat plus heat of melting. Therefore, melt fraction is L is equal to Es by Em, which is P V naught alpha minus 1 upon twice of Cp Tm minus T naught plus Hm. And we also have the condition that the pulse duration Td is pulse duration must be greater than or equal to solidification time plus Tc, which is the cooling time. So the material must melt and resolidify and come back to its original state. So from this very rudimentary, not exactly rudimentary, but the basic, the simplified theory given by Schwartz, wherein we are assuming that all shockwave energy gets converted into thermal energy, that in turn leads to melting. that melt fraction that we can get from Schwartz, if we are to plot, this is normalized energy, and this is normalized shock wave duration. Put 0.1 to zero point 0.4, 1.2, and here you have 0.01 logarithmic scale 0.1. Those two factors lead to a plot that looks like this. So you have, this is the minimum melt fraction, and this is the minimum shock duration. So this is the region that we expect good consolidation to happen, and the shaded regions are basically regions where consolidation happens, and the hollow regions are where consolidation is not good. So this is the dynamic consolidation for AISI 9310 iron powder. Okay, so this is how it looks like. So yeah, this is what we have. Uh, in case that this basically wraps up the shock consolidation of powder, and you could also have phase transformations occurring in powders. You can also have other applications, particularly in military, which would be like armor penetration or defense against projectile, stuff like that. So like both sides of it, attack and defense. And you could look at that in more detail, but for that we need some more background that we have not been able to cover in this lecture. The Mark Mills book, apart from this course, whatever we have taught, there are a few topics that you may get into. So very good, at least starting point, if not like the ultimate reference. You can learn a bit, and then you can use the references provided in the book to go into even more detail. Okay, so this wraps up what I have planned for today's session. It got a little early. Uh, so either this session, so this application, this may not be exactly part of in this may not be the primary focus of this subject. But apart from this, if you have any other doubts in any of the classes that we have covered so far, so I think you have around 10 more days, 10, 12 days till exams. So if in the meanwhile you have any doubts that you wish to ask me, you can post it on the discussion forum, or yeah, try to, I will get back to you on those. Okay then, thank you and good luck with your exams to those of you who are preparing, and hope you learned something new in this course. It was a privilege for me also to conduct these sessions, and I hope I have not led you to more confusion, but to a little more clarity. Thank you.